and good afternoon, everyone. So my name is Atif, and the talk that I'm going to present and discuss might sound a bit research-oriented, but I'll try to tie it back into the Python, because that's the programming language that I usually use, and across the projects that I manage is the de facto language that we utilize. So I'll share the experience as well as a bit of the mixture and the packages and all that comes into play when we do research projects using Python. Okay, so the talk, a little bit about myself so that you could know like who I am and perhaps where I'm coming from and what's my motivation. Of course, about the talk and then definition, ideas, some of the essential technologies that we utilize, of course, mainly pivoted around Python, and then the project description and where Python was utilized. About the talk, so it's about a project that we did for a COVID challenge that was there when COVID was there, like it was funded by SFI. We created a project that was utilized by the likes of Health Services Executive, HSE, who was a partner in this project. The idea here was like when we were challenged by COVID, the researchers didn't know much about what to do with it, right? We didn't know where does the solution exist. And the thing was, the best hope was like there are health practitioners, researchers, we want to help them with some sort of a telescope, like you're looking for an object in a distant space or something microscopic. Can we speed up the process of finding something meaningful? And that's where the idea kicked in. And the idea was to build an exploratory search system, which would be different to the search services that they already have. And the main motivation was to allow them to navigate scientific literature at a much faster pace, with much more results, with much more diversity in it, and the ability to find something different, which they are not able to find through a standard search service, for instance. So that was the context. In terms of my background, I come from a computing background. I have a PhD and master's and bachelor's from there. I've done 3 postdocs in applied research, so I'm quite active in research. I'm now a faculty at business, a faculty of business. The reason being, like I've seen like computer science has a lot of value to satisfy the needs of the business, because we are all the time looking for satisfaction of the users and all these kind of things. In a way, they are our clients as well. So that motivated me to apply computer science in the context of business, because that's kind of a natural marriage that we can seek. Some of my research areas are like data analytics, machine learning, text analytics, social good, and business analytics. So you may define me as within the space of computational business and social science person. So I believe in transformation through digital technology. That's where I'm coming from in terms of my degree and background. In terms of my motivation, that comes from the point of view of building a healthy world, empowering humanity, causes of social good. Now, to set the tone, what's a search engine? So we know we have used Google, we have used Bing, we have used the likes of Yahoo before. So search service is basically a software that is designed to carry out a simple web search or look for the documents that you're looking for, and then allow the user to see a snippet of the result before they hit a click. And the snippet needs to be very related or relevant to the search query or something that the user might be interested in. That's the underlying assumption, but the real challenge has been on the search engine, and that has been like over decades now, like at least 20 years. How can we think of a new search service which doesn't really rely on 10 blue links on the first page? And there are jokes like this in information retrieval community, like if you want to hide a dead body, hide that onto the second or the third page of the Google search, because nobody's going to look over there. So the main thing is, like, if we are contrived or we are restricted by this challenge, think of the likes of the health services who were challenged by COVID, that you are just seeing 10 blue links. And if you want to scan further, it's not very motivating. Can we change something? Can we do some innovation in here? So that's where the context of search engine is. And the other concept or the other idea that we talk about is, we do a bit of magic through the search services, but there is another field that has been developed over the years, which is called artificial intelligence, where the idea is, can we make machines to think? can we give them the artificial ability to help human with the decision making? Now, the thing is, if you look for a search engine community, which is information retrieval community, they have been working independent of the AI community for long enough. Of course, there are now bridges between, there are interconnections between, but they have been traditionally different, right? However, now we make use of it. So the idea here was, can we bring something from AI and innovate something into the search service? So again, to rephrase the challenge, can we combine search engine and AI to address the challenge of COVID-19 to facilitate health practitioners, right, who are dealing with the challenge of COVID-19? And COVID-19 is just an event, but here the idea is like, something like this can happen again. If there is a disaster, if there is a catastrophe, if there is an issue, something similar to the likes of COVID-19, it was a kind of a wake-up call. Can we come up with the technology much quicker and find a solution much quicker, right? So now here is another thing. However, when we marry between search engine and AI, there is again a challenge of like, however, the users may still wonder why an AI is recommending something, why such an inference was made. This is kind of like, can we make AI a bit transparent? That has been the goal of AI from like last 5 years or so. But this gave birth to the idea of XAI. So the challenge here was like, you have standard training data, you have machine learning algorithm, they learn a function that makes a decision or recommendation, and that's all what you got. That's what a standard AI would mean. The user, though we believe, is satisfied, but perhaps is not truly satisfied in the likes of legal challenges, medicinal challenges. These kind of challenges where the impact is so significant that you have to become accountable and transparent with your judgment. So why did the system say something like this? What could be done otherwise? When do it succeed? When does it fail? How can I trust the decision? How do I correct an error? And these kind of the questions were not really the questions of AI. The change happened, and we are entering into the area of XAI. Here, after the GDPR, there has been a huge push towards XAI within Europe and as well as globally, where the idea is you have the training data, you have the machine learning process, but now what you're adding is explainable model, explainable interface. So model needs to be explainable, and then the UI needs to be supportive of that as well. So once this ideally happens, the user hypothetically says, I understand why. I understand why that wasn't the decision, the other decision, and then why it would succeed, why it would fail. I can trust a little bit more, and I know where it erred. So that's kind of the motivation, right, for the XAI compared to AI. Now, when this was all happening, COVID just happened. We were in the infancy of XAI, and COVID just happened. So this project came from the idea of some crude thinking around XAI and search interface and getting rid of the 10 blue links somehow to speed up the process of finding something interesting. Essential technologies that were utilized throughout this discourse were like this. So, of course, to develop such a system, we had to come up with a quick solution within like 6 months' time, even much earlier than that, because it was an iterative solution that we were promising to HSE, and their feedback was incorporated as well. So we wouldn't wait for something to get developed in 6 months, but rather we will have an MVP much earlier, and then incorporate it further. So that's where Python was the main programming language. For the search services, we utilized Elasticsearch, which is a search service that will provide us with the search engine, the standard search engine capability, and the support that exists within Elastic. Django was utilized as a web framework, which is, of course, coming from Python. DBpedia was utilized because that's where we can pull a lot more information from in terms of the Wikipedia. So DBpedia was important because a lot of edits were happening around Wikipedia, and there was a lot of embedded information in the category graph structure and article structure around different concepts that would be medicinally or otherwise important and relevant. So that's where we benefited from it, besides the medicinal taxonomies, which is another separate thing. Network X was utilized, which allows us to navigate over a graph, which is supportive of AI. Ginsem was utilized again, like it's a topic modeling library, again coming from Python. These are all coming from the likes of Python. Scikit-learn, Spacy was used for NLP. Med7 is an information extraction model for clinical NLP in AI. Again, all available in Python. SparkQL wrapper, which is utilized to query SparkQL, which are remotely executed services for DBpedia. And then Bootstrap, which is simply a CSS framework directed at responsive interfaces. Now, just to remind the challenge was a lot of research gets published. At that point of time, a lot of research was getting published on daily basis. Which one is good, which one is related to what? To keep up with the speed of it was a real challenge, right? So there was an issue of information overload. To keep up and explore articles on COVID-19 directly or indirectly, we need something to quickly showcase or show what is important, relevant, otherwise diverse, but everything perhaps. So that was an issue, right? You need to be mindful of what's happening. So the motivation was to assist the COVID-19 focused researchers in life sciences and healthcare to understand the pandemic in terms of by presenting them an exploratory IR or information retrieval system, which was called RCES. So the solution that we came up with was the system that we developed or employed utilized a technique which is a published technique called EVE, which is an explainable vector-based embedding model that was utilized through the process. So we didn't invent a new model because we didn't have much time, right? Using DBpedia, but we made an adaptation. We adapted MESH, which is medical subject heading taxonomy, besides DBpedia, to exploit the concept relationships and the medicinal terms and their implications and their meanings and all that. The first thing was we want to increase the search space and then arrange them into different topics and headings to allow them to explore and exploit. So we developed a lot of various query expansion techniques, along with some nuggets of explanation, which we call facets, that would collectively, form the rapid queues or information to be, assigned to a queue, and then users can navigate through the facet. And I'll show you what it is. In terms of the EVE, we utilize SparkQL and DBpedia, which has a package. Both have packages in Python. In terms of facets, the two things that were utilized were Network X and Bootstrap. Strength. Okay, so when a query is expanded, what it means is you are asking for many answers. So you're asking for increasing the result set. So this is kind of like what we want to do. We want a diverse result set because we don't know where does the solution exist. So we must incorporate certain techniques, different techniques to expand query so that it could be interpreted in many different ways and suggest some of the additional terms so that the result set could be increased. Now, when we do that, we have to keep in mind that it doesn't cognitively overload the user. So that was, where there's an opportunity, there's also a challenge. So this will help, in a way, researchers to actually look for diverse result sets. But if you expand it too much, how many results are you talking about? How many results can a user see in a split of a second or perhaps in a minute or two? So that's another challenge. Another thing was we thought explain how the query expansion took place. Because if we explain, we can hint the user who is using the system to understand why we are retrieving additional results and how we are retrieving those additional results. Not just expand it, but explain what does expansion look like. So added some terms along with weights and booleans to control the query which was expanded. So this kind of brings an explanation bit into the equation. Then UI and explaining machine learning intelligence. So finally, arrange the result sets along with facets, which are the queues or the key terms under which different results are arranged, linking those result sets in categorically called facets, which is a post-retrieval step. Now, if I have to show the architecture, so the data sources, as you can see, are coming from standard, PubMed, medRx, Elsewhere, Archive. This is where we were pulling the results from, where the published research appear quite quickly, right? Besides that, of course, so there is an article crawler that was written, which will collect the articles. Here we utilize Python and data sources API that were available for Python anyway. So this is where we prepare the data that was alive, of course. Then for indexing the articles, we utilize Elasticsearch because we have to perform a search. Then that index was queried or could be queried through web interface, where there are different query methods. Then we would highlight certain results and arrange some queues. So when we do all the query expansion bits in this layer, Python, Django, DBpedia, Mesh, SparkQL wrapper, NetworkX, and other AI-related Python packages were exploited to our advantage. Again, this happened because there is tremendous support that is available in Python to develop something like this much quicker. In terms of once the query methods are selected, the results are refined, the web interface then refined highlighting and refined queues. So it's more about retrieval and ranking and presentation there. Here we utilize Django and Bootstrap and Python. So this is how the system actually looked like when we developed it. So up there you can see there were different criteria, different sources from which the user could select who happens to be a medical practitioner, such as I want to expand the query using Mesh synonyms. There is like synonyms as well. DBpedia, which is analogous to, which is structured Wikipedia in a way. Synonyms and different rule-based approaches, which was linked to the user's profile. So user may come from psychological, maybe coming from surgery, or maybe coming from some different backgrounds, and they might have their own taxonomy, which they tweaked around. So this is what we call rule-based expansion, which the user can control through their user profiling. Of course, time and date, then you can say whatever queries you want to. Then you can talk about whether the retrieve article talks about dosage, drugs, duration, whether the form was discussed, route to which the treatment was take place. Was there any mention of the strength over there, trials, or the review article? So users could click on these things when they are looking for some search results. And when the expansion takes place based on the query that was issued by the user, such as influenza vaccine and COVID-19, just to motivate with this very simple example without relying on some complex medicinal terms, you can see Mesh would retrieve some other terms that were related to it. Was vaccine, then there was influenza, again repeated, and there were hepatitis, and so on and so forth. And there were, again, the strength of association that the system thinks which is related to these terms, which were not issued by the user, but was found by Mesh. Likewise, for DBpedia, you can see somehow there was a relationship between COVID-19 somehow. I'm not saying scientifically whether it is correct or not, but there was some correlation between animal virology and COVID-19, and so on and so forth. So it was able to say, like, what's the strength of the weight, and all these explanations were given, how it inferred. And from the rule-based approach, after understanding and the user's profiling, this is how it was expanded as well. For example, there was like COVID-19 or severe acute respiratory syndrome, coronavirus 2 or something like that. And these kind of like different expansion terms were automatically inferred. In terms of the facets that I was mentioning earlier, so it would pull, like when you have so many query terms, so of course the result set will increase tremendously. Now the challenge would be, how can we show those old results in a small limitation of one single page? So here we then, on the basis of like 200 and 300 results that were there retrieved from the top result set, we would arrange them back into 15 keywords that were inferred on the fly, rather than strict 15 keywords, which we call queues. Again, this kind of explains how the results were discovered and arranged back. So for instance, it says there are some results around vaccine, infection, analysis, severity. There is a word like potential, influenza and protein and all these kind of things. Now, in here, when you see the result, you could see here, for example, it would say, influenza vaccine is a type of drug, and all these kind of things were labeled based on these selected options. So if by default say like I want everything, so everything will be highlighted, you don't have to tick everything. But if you tick on one of them, only those will be highlighted. So that was kind of how the user wanted it. This highlight that you see over here of the vaccines was actually done through Spacey and Med7, which has a great support for that, again, coming from NLP. In terms of the query expansion, the idea was like to increase the recall, means if there were like 20 results, we want 200 results. It helps people in science to explore and exploit. The danger is you have too many documents, but then the challenge is how would you arrange them, which is where we look for the keywords to arrange them back into those 15 keywords, right? If you click on those keywords, the results will shuffle. Different number of query expansion strategies help the user to pick the one that works best and suit them. And of course, if they want to modify that, they can utilize their user's own profile and personalization, and then change how the way expansion was took place. So mix of strategies and different strategies as suits for the type of the query and task. Help with the completeness of the result because of the query expansion. In terms of how it was exploited, of course, I can give you an idea of how MASH works, but I would utilize something which is very common among ourselves, is Wikipedia, which also we use to our advantage. So Wikipedia has, articles that has inlink and outlink. So you can see all these inlinks and outlinks, which we could exploit. Those articles are then related to categories, and those categories are then inlinked and outlinked within themselves, which we can utilize. So imagine if there is an article on COVID-19, there could be other articles that would inlink to it, and the COVID-19 article would outlink to some other related articles, and as well as it would be under COVID-related categories and their own structures, which we can utilize to expand the query. For example, like diseases related to children. Of course, there would be children category, and then diseases related to children, and then there could be expansion taking place if we were to exploit it in a correct way using Wikipedia graph structure. To give an idea, again, we adopted Eve strategy, which is a published article. To give you an idea what Eve can give you, if you have a query phrase, what Eve would do for you is map that query phrase into Wikipedia categories and as well as articles to find the best match, first of all. Using that, it will find other associated and related Wikipedia articles and categories in terms of how closely they are related to that article or category that was matched in the initial. And then present you with a vector of knowledge. So for example, if query was around pasta, let's suppose if that was the query, it will find, Eve would find and give it a score back, like it's a type of a staple food, Mediterranean cuisine, and so on and so forth, other related things. So imagine if it was COVID, if it was a certain medical condition, then other related concepts will be pulled from Eve strategy. What you see over here, it is an adaptation of Eve on Wikipedia. However, in a similar way, MASH is also arranged, which is medicinal taxonomy, where there are medical terminologies as well, which again Eve could work on because it's a hierarchy as well, it's a graph. So this is how the flow algorithm would work, which is inspired by the page rank, where the propagation of the scores will take place. So if this is the initial matched concept, it will flow, the score uniformly into the category structures, for instance, and again, similarly, it will flow the same kind of scores into the articles that inlinks and outlinks to that particular matching concept. And then it will diffuse. So of course, it won't run forever, like it will just run for two immediate neighbors of the parent concept, which was matched. So once that happened, we then utilize this to our advantage by using the idea of facets. These are essentially extracted topical terms that represents information extracted from the retrieved result sets that would bring and tie them back into the retrieved result set. So here we adapted a biased PageRank model, which would look for terms that co-appear in an article, and then create, edge and node concepts between them, and then pull out which was the most dominant term, or the most popular term, or most important term, and use that to generate facets. So it's something like PageRank would discover the most important page. Here we would use 200 articles, for example, from the top matching results, which is the most important term that appears, and that gets the first facet name. And likewise for the second and third and fourth. So that's how we would utilize the diversification. Again, here, standard Python was used and NetworkX was used, which is a package in Python to do this. So adaptation, just to give you a context, how does PageRank work a little bit. So again, the package is NetworkX, NLTK, because we are doing tokenization, stemming, and stop word removals, DBpedia, and Mesh, because we want to deduplicate the concept. If it talks about child and children, we're supposed to treat them as one. If it talks about influenza and flu, we are supposed to treat that as one. So deduplication takes place using this. And then SQRL wrapper as well. SPARQL wrapper as well. So how do we do that? Noun phrases were extracted as the node concepts from the retrieved result set. Then nodes were deduplicated. For example, such as flu and influenza are treated as one, instead of having them as two separate noun phrases, by exploiting the semantics behind that using DBpedia and Mesh and user-defined rules. Edge is how close those terms co-appear in the document within a certain window distance. So it's an inspired technique. Now, using this, an edge exists when they co-appear in a window distance. We utilize a strategy to score how much the edge should have a weight based on inverse of the distance of the noun phrase from that term. So for example, like if vaccine and influenza appear very closely together in a document, like influenza vaccine, for example, like that, for example, or influenza and vaccination together, we would say it receives a higher edge weight compared to vaccination and influenza if they are happening in a sparse locations in a document. The significant terms retrieved, it's a chi-square test, which we run to identify which were the significant terms compared to the retrieved result set is coming from IR theory, information retrieval theory. Then we normalize the frequency in terms of the document frequency so that the popular term versus the rarer term being informative. These are all IR-based theory. And then evenly distributed retrieval scores to the documents. So just to motivate you, how does PageRank actually works so that you get a bit of an idea. It's a very simplified example of this. So it's a simplified example without taking care of the damping factor, which is kind of a parameter within a PageRank. So imagine that we are looking for the score for, let's suppose, node number 5. So initially, we assume that all terms or all nodes get the same score. So if there are 5, everybody gets 1 by 5. Then you look for who inlinks to the 5. So 4 inlinks to the 5. So the score would be coming from 4. So for how many times 4 outlinks? So 4 outlinks just once. So all of the score that comes from 4, which is 1 by 5, is added. Likewise, if there are 4 outlinks, for example, in the case here, we then, for example, 5 receive 1 from here, 1 link from here, and 1 link from here. So if you see, like in terms of here, 3 gives 1 outlink, another outlink, another outlink. So 3 gives 4 outlinks. So therefore, 1 by 5 into 1 by 4th of the score comes into 5. If all others are giving just 1 score towards 5, 1 outlink is existing, then of course all of the score flows from there. So it's like, who do I vote for? And if I vote for 3 people, my vote gets divided into 3 of them. If I only vote for 1 person, then that 1 person gets my full vote. So that's the idea, and then it keeps on propagating until it gets saturated. And that's how you get the PageRank score. And finally, if you run it over time, you will get to see that the best score that gets received in terms of the final rank. So the 5th node gets the most important because it gets many votes directly or indirectly from other nodes. That's how the informative node is discovered. Again, for vaccination or medicinal term, different terms mention each other. So which term gets most of the vote in terms of the context of the query, we get to discover the most important noun phrase that represents that query. And likewise, bit of diversification over there through chi-square as well. So this is how it then looked like, for example, if a user clicks on influenza, for instance, for example, one of the facets, influenza, then you can see only those results will be shown that are related to influenza. And also it would highlight where influenza was discovered. So indirectly you can see, it has highlighted flu and it has highlighted influenza. You can see flu and influenza for the system means the same thing because they are highlighted when you click on influenza. So it kind of tells you how the synonyms were also extracted. So the nature of the development for this kind of a solution, and again, thanks to Python that has so good support in terms of the libraries and packages, that we are able to generate a quick solution. If you were to use some other kind of perhaps programming library or programming language, we might not have that quick turnaround. So the nature of development was iterative, fulfilling health practitioners' defined criteria. They were not even sure themselves what they were looking for. So again, we had several rounds of meetings with them. We show them something, were they happy with it or not, and we bring in other solutions as well. So the idea here was not just to give them one solution. We were not looking for giving them just one fixed solution. So therefore, different query expansion techniques, and even allowed them to have their own rule-based approach, which was tied to a user's profile, which could be initiated globally if that was a surgeon versus if that was a neurologist or somebody else. And the idea was think about aiding human rather than replacing the human from the loop. So we were not trying to replace the human. So that's the key point over here. Whenever we adopt AI or XAI, the idea is never to replace a human being, because AI, it's very hard to say would ever be able to completely replace a human. That's far-fetched. So the idea was we are not replacing, we're just being a telescope, which again needs a human being to see behind the lens of the telescope something beautiful and interesting. So these are the references of the published works that are over there. There is also a demo of the system if you want to see. You can take a picture which you want to see. Of course, you're welcome to see that. If you're interested in doing research or PhD, of course, Ireland has a great support for that. So there are funding calls if you're interested, anybody. If you find some research fascinating, you can contact me if after the presentation and questions, if you still have some questions, you can contact me and reach me out. Thank you very much.
Hey, thanks very much. Correct me if I'm wrong, but did you treat PageRank as the only or the main factor in determining relevance?
Right. So in terms of calculating a facet, if I go back, this thing, we exploited PageRank. But in terms of the query expansion, the methods were very different. For example, we utilized Eve that I introduced early on.
Sure.
So there are two things at play. One, how to expand a query and generate some explanations. Second, once you have humongous amount of results set, how can you arrange them back with 15 keywords that you can pull from those? So when we are pulling the 15 keywords from the result set, we adapted PageRank. But when we were expanding the query and explaining what the query expansion meant, we utilized Eve.
Sure. If you could backtrack to the part of Eve, so you're only using PageRank for faceting, not for determining the correct answer.
No.
Yeah. So this is like scientific literature. It's not pharmaceutical literature. It's not the open web. But how do you avoid the effect where the document that has 500 citations, or has a large marketing department behind it, is judged to be more relevant than a really good document that may have 0 citations?
Right.
How do you guard against that?
Right. So because if you were to see in the context of COVID, that meant nothing at that point of time because humongous amount of research was published. A lot of papers get citations, but when the science becomes stable, a lot of papers will also pull back, right? So citation criteria was not that effective in the early on setting if we're not going back into the history, right? So from that perspective, in this system that was promised within the 6-month cycle, we didn't include the citation. But of course, later on, when there is a second phase of the project, which is not just related to COVID-19, which is related to, the other medical articles. General purpose articles, which is utilized for their library services, for example. Over there, citation does play a factor. So, yeah.
Right, but my question is, how much confidence are you saying that the number one result or the top 10 or whatever from your search engine will be the most relevant?
In terms of the query need. So it's more like...
Not linguistically relevant, but like the right answer to the question.
Yeah. So it's more like linguistically and semantically. That was the idea, because we wanted to find something which researchers didn't know already. So they can think about whether it's related or whether it's not related, whether there is a hint about some article that they missed out on. Because finding something which was top cited, they were getting that already from their search interface anyway, because of the previously developed search services that they already had. Yeah.
But it's not necessarily the best research, it's just the one that prima facie appears to or claims to be the right answer.
Yeah.
So did you do any like trajectory analysis or anything to determine, which papers are overhyped and oversighted?
Right, for this project we didn't care about that.
Right, so it's generally known in academia that you have citation rings.
Yes.
Professors and their PhD students citing cliques, and you can draw the Facebook-like graph of the cliques that cite each other and don't cite each other.
Yep.
So how do you guard against those sort of known pathologies of citations in literature?
So, I don't want to give one answer, but I'll give you a hint around that. So it is kind of a spam problem, right? Where we have done the same kind of a challenge that we have treated in the IR community. For example, you see link farms, for example. We call them link farms in the IR literature. I think this is the same thing that is happening when you have cliques over there. So again, the different anti-spamming techniques could be adopted for that, but that wasn't the case for this project. But if we were to incorporate that I think would be the strategy to go with, yeah.
Right, except when the spammers may be multinational pharmaceuticals and their research departments that take large amounts of sponsorship.
Yeah, and then we have to be very careful of not saying somebody is a spam.
Yes.
There will be ethical implications around that too. Yeah.
Okay, thanks so much.
Any questions? Maybe one more?